Professor Edison Silva, who is going to talk about search for new electride high-temperature superconductors.
We need to dress. So. Good morning. Thank you for being here. I'd like to thank the organizers, Alexandre and all the organizers for this opportunity. And I want to talk to you about a search for new electride superconductors at high temperature. So what I want to talk to you about is about this material, lithium-5 carbon, which is electride and only exists under pressure. It's a prediction of ours, and I will explain that. And then I will talk about a two-dimensional material, which is moly-2 nitrogen, that shows superconductivity at ambient pressure. And since the focus of my presentation is superconductivity, I will give you a brief review of superconductivity, so you understand what I'm going to do. As you know, superconductivity has 111 years. And what happens was that Camelin Onnes, months before this date, lowered the temperature of mercury to 2 Kelvin, and he found zero resistivity. And then many months after, on this date, he decided to come here at 2 Kelvin and start increasing the temperature. And he did that, and nothing happened until he got to 4.19 Kelvin, and then he saw the transition. So that's how he found superconductivity. Having done that, everybody decided to, I'm going to solve the problem of superconductivity, but a few important ingredients for superconductivity were not known at the time. The second important aspect is the exclusion of flux, the Meissner effect, that is very spectacular. And the London brothers explained that, showing that the magnetic field that was constant outside would dump with this distance the penetration depth of the superconductor and would produce this Meissner effect. This result is a very, very important one because this is the precursor of what's called the Anderson-Higgs mechanism of creation of mass of bosons. And the third important point was that TC depends on the mass of the atoms. So it has to do with the vibrations, with the phonons. Well, with that, in 1950, everybody trying to solve the problem. A few years later, Bardeen, Cooper, and Schrieffer came to a solution to this problem. So Bardeen asked his postdoc, Leon Cooper, to study the problem, see if he could come with some interesting results. And what Cooper did was to consider 2 electrons on the Fermi energy and consider that there was a very weak attractive interaction. And when he did that, he found a bound state that had this expression. So this lowered the energy of these 2 electrons, giving them a bound state. And you see, this appears in 1 over V, the interaction. So this doesn't come in perturbation theory. So the idea is that you have 1 electron coming in. It polarizes the lattice. The other electron, the second electron feels an attractive interaction that's mediated by the electron-phonon interaction. So out of 2 fermions, you get a boson on a singlet state. So the energy was here, the Fermi surface, at the Fermi energy. It lowered to that value. So the energy is lower, and also there is a gap to break this. So this state is protected by this gap. OK, with that, they wrote another physical review letters where they show that this has to do with phonons, electron phonons. They wrote down the wave function for this problem, and then they solved the problem And it's a 30-page article that does everything that needs to be done to explain a superconductor with very weak electron-phonon interaction. So the situation was that you had these experiments, you have the theory, we are here. BCS theory explains superconductivity. And the results that they got was that you have the gap, you have TC, you divide the two, you have a number. This is a signature of weak coupling superconductors. So you have the phase diagram here, TC. For that, they received the Nobel Prize, very well-deserved Nobel Prize. But here, there is a problem. This theory is very nice, but how do you go beyond that theory? From the paper, it's difficult to do that. But then the Russian school, because of von Gorkov, using Green's functions in many-body theory, wrote the equations that explain all that, and that could be used to go and do extensions of this theory. And one important one that I want to use is the Migdal-Eliasberg theory that considers the electron-phonon interaction to all strengths, go to strong coupling superconductors. At the time, this theory is beautiful, but there was no way of solving that. There was no very accurate electronic structure or phonon structure calculations at the time. So people resorted to finding some phenomenological expressions for transition temperature. And even that, at that time, needed some experimental input to calculate. And what happens now is that now you can do Eliasberg equation within the modern DFT theory, and you can be predictive in superconductivity. So just to tell you what it is, lambda, this parameter, the Eliasberg parameter that is the information of how strong is the interaction, has to do with the electron-phonon matrix elements and the phonon spectra, all in frequency. And at that time, those are the two expressions that were produced from the theory of Allen and Dines. And now we can calculate this very well using the ideas of electron-phonon or the DFT. Now, when I say modern electronic structure, I mean the things that happened after 1980, in the 80s. Nicola Marzari has this beautiful article that he explains all these methods that I use that evolved from this. It all started with pseudopotential, the ab initio pseudopotential of Marvin Coyne. So now you have superconductivity with the capability of predicting new superconductors. What I want to talk to you is about electrides. So what's an electride? Everybody knows what an ionic material is. You take sodium chloride, sodium gives one electron, everybody's happy. This is an ionic material. Now, if you take lithium, one electron, and carbon, and if you take 5 lithiums, 4 electrons of this lithium are given here, and the system is happy, but there is one electron left. And this electron lives in the interstices of the material. This is an electride, okay? So, is this real? Yes, there are many examples of that. You can have two-dimensional gases. You can have tubes, one-dimensional tubes, and you can have atoms without nuclei in the interstices of the material, which is this. One important case is this one. It was a prediction. This two-dimensional material had a free electron gas here, and that prediction is 2014. 2016, it was measured and seen, this behavior. Okay, I want to talk about superconductors. So before we got into this game, there was this result, this lithium-6 phosphorus. Its transition temperature is 39. It's at 270 gigapascal. I have to say that since the beginning of superconductivity, studying superconductors under pressure is one of the lines, very important lines of research. And in this century, when it's possible to do these experiments, it's very intense. So these people, they did the Eliasberg lambda calculation. That's that spectra that I told you, the lambda. And what they do phonons to show that the material is stable. And they show that the electrons reside in the interstices of this material. So this is an electride. Now, we are going to search for electrides using the particle swarm optimization, which is a method based on these beautiful choreographies of fishes and birds. This is implemented for electronic structure calculation of stable structures. And the method is called Calypso. So these things that I'm talking about are measured in the laboratory using this DAC, diamond anvil cells, two diamonds that are pressed and gives the pressure to this material, and people can go to 500 gigapascal. So this is done using VASP for the calculation of the structures. So you have a lot of structures coming in, many generations of this calculation. In fact, 1,500 structures were studied here to produce this material that is an electride, as I will show you in a moment. You see this material is hexagonal. This is the top view. This is the side view. So you have a plane of carbon and two different planes of lithium. And the action occurs here. This is where the electride state lives. So looking at that plane, if you look at ELF, the electronic localization function, you see that this interstices here is where the electrons are. You can also look at the charge density difference that shows also this network of states. Here's the isosurface of that, and this is the isosurface of that. Is this really an electride? Well, we did an exercise to check that, which was to calculate this, electronic structure with one less electron. When you do it, one less electron, all the other parts of the Fermi surface are similar, but those states here, they vanished. Okay? So the electrons that are near the Fermi energy are electride states. Another way of looking at that is if you look at the integrated density of states from one electron down from the Fermi energy. And so in this window of one electron, you calculate the density of states, and these are the states, interstitial states, and this is the tube, the network, the two-dimensional network. If you do, again, one less electron, that thing disappears. So the material is an electride. This material only lives at finite pressures. It doesn't live at ambient pressure. So we looked at phonons, other things, but I will just talk about phonons. So phonons from 40, we didn't expect this to be stable, and went all the way to 230 GPa. And here, these two pressures, the material is unstable. But from 50 to 220, it's stable. All the phonons are, there are no negative phonons, so everything is working. And the focus of everything is that particular point here, but I have superconductivity in all of these pressures. So here, I'm showing you the electron-phonon interaction spectra, the 2 alpha, 2F, for 50, 100, 150, 200, and the lambda, the electron-phonon parameter. And the electron-phonon parameter increases with pressure. So I'm going to the most important case, which is the 210 GPa. The electron-phonon interaction is 1.25. It's a strong electron-phonon interaction. And we calculate the Macmillan and the Allan-Dines expressions. I have to say that Macmillan was the first approximation. The Allan-Dines is an improvement on Macmillan. And if the material is isotropic, which is the case that I'm talking about here, this results, if you just want the temperature, the transition temperature, you have this point, if you calculate the full Eliasberg equation, it will probably come on top of this blue line. Okay, so we have this material, shows superconductivity starting at 13 Kelvin at 50, and at 210, it gives you 48 Kelvin. Now, those are materials that have been studied in this century. These are experiments. Every result has the pressure here. You have 500 GPa. These are predictions. That was the top prediction before we did this work. And now, in our calculation, we have lithium 9 Kelvin higher and 60 gigapascal lower. Okay? So this is the highest transition temperature for electrides under pressure. So that was published in this publication here. And we had this nice highlight, which is that cover. And we are happy with these results. But then after that, so these results that I showed you are predictions. Okay? This material was not produced yet. We hope that somebody will do that. Now, I want to talk about moly to nitrogen, two-dimensional moly to nitrogen. And so it's this material here is nitrogen sandwiched by 2 layers of molybdenum. And we are going to look at density of states, electronic structure, bands, density of states, the gap solution, the Fermi surface. And at this case, in 2 dimensions, this material is anisotropic. So we have to go beyond calculation of TC. So in this case, we are going to go for the full Eliasberg solution, which is that I will explain in a moment. And when we do that, we look at the sheets of the Fermi surface that contributes to the superconductivity. And this material is a superconductor at normal pressure, but being a 2-dimensional material, it's interesting to study it under tension, see if we learn a few more things. So we did that. Now, this material, like I said, is a real material. It was produced in 2017, and there was some calculation in 2020. The experiment, you see, before, moly to carbon was known, but moly to nitrogen was only produced in 2017 due to a process called ammoniation that changes the carbon to nitrogen. And this group, they studied many of these materials, 2-dimensional materials, looking for superconductivity. And what they did was to do the electronic structure and calculate the transition temperature. And they came up with a temperature of 16 Kelvin for moly to nitrogen. We decided to look at this material. And for that, we used dense functional theory, quantum expressor, dense functional perturbation theory to do the phonons and the electron phonon, maximally localized Wannier functions, because you need a very dense grid to do this calculation, and calculate the anisotropic Eliasberg equation. So the material is a layer material, but there is just the monolayer, and we are interested in the monolayer. And like I told you before, in the other case, in this monolayer, we have an electron gas here that is the electride state that's called electrane in 2 dimensions. So we have this network of charges flowing here. And here, if you take a plane that there are no atoms, you find the electride state. Like I said, we are going to study this under biaxial stress. So the Fermi surface of the normal material is this. As we strain, it moves. A new sheet comes here. So we found many interesting aspects in this problem. And one point that is important, so here again, the network that we are talking about, this electride state, it amounts to 30% of the states at the Fermi surface. the Fermi energy, which means that for the superconductivity values that we are going to get, this 30% is very important to have a higher transition temperature. So we looked at the bands as function of stress, relaxed 1%, 2%, 3%, and the bands move due to the stress. And interestingly, this band moves and goes to the Fermi surface, which creates a new Fermi surface there. We looked here. The first 4 important bands are separated, and these are the sheets of the Fermi surface associated to them. So you see this new state come here. So everything seems to be interesting. We looked at the phonons for this material, and the phonons are stable. And more than that, we have the phonons, and also when there's these red points here is where the electron-phonon interaction is important. Having that, we decided to look at this intermediate question of how lambda behaves in this material as you stress the material. And what happens is that the lambda goes down up to 2% and then starts going up. And here we can check which are acoustic or optical phonons. The optical phono, the acoustic phonos don't, the optical phonos don't change that much. The action has to do with the acoustic phonos. Now, having that, we can calculate the full Eliasberg calculation. And if you do isotropic Eliasberg, you have this red line here, and this red line here. This is relaxed, this is 3%. Now, if you do the anisotropic theory, the delta for each temperature is a function of energy. It has a distribution. So one extrapolates a line to get the gap transition. And here it gets to 24. And this thing have to do with these parts of the Fermi surface of the material. As we change from relaxed to 3%, you have these new states that I showed you before that contribute to a different situation. One important point is that here there are 2 gaps intertwined. This material, this anisotropic material, is not a single gap superconductor. But here you cannot see. But here, at 3%, you have the main gap here and the other gap up here. And I can show you that before. Now, with all these calculations, what we did was, this is the transition temperature, Allendine's transition temperature, calculated with those expressions that I showed you, giving 18 Kelvin for ambient pressure. The isotropic calculation, that red line on the previous slide, is that. And the full show, which is the anisotropic calculation, give you this line here, which starts at 24.9. So the material under strain gives these results. Now, having the Eliasberg equation, one can calculate the superconducting density of states. That's something that from the beginning, when you have a material, people measure the superconducting density of states with the IDV, and the theoreticians calculate this. So for relaxed material, the gap is 6 milli-electron volts, but there is a little blip here, which is that other gap that is intertwined with this, with the main gap at normal pressure. But when you go to 3% strain, the main gap goes down, but another gap appears outside for higher energy that I showed you in the previous slide. So that's the story of this material. I think by studying the material under strain, we learned a lot of how things behave and how they give this kind of evolution. So, like I said before, last year we came up with that result. With pressure, everything here is with pressure. Now we have another point here that is lower temperature, but it's at ambient pressure, no pressure. The only one at no pressure. Okay? So this work was published at nanoscale and had this feature. And so, in conclusion, what I showed you is that we looked at superconductivity at pressure. We looked at superconductivity under tension for two-dimensional materials. And in this process, we learned a lot of things, interesting things that at least I found interesting. And to finish, these are the two gentlemen that did a lot of the work, most of the work, my former students, Zena Pereira and Giovanni Facin. And we had this support. We used the computing facilities of these centers, in particular the new Ada Lovelace machine at Senapad. And with that, I thank you very much for your attention. Thank you. I'm open to questions.
Are there questions?
Thank you, Edison. This approach to use the DFT calculations and the Eliashberg equations are very, very interesting, I think. My question is, how general is this? Can we use it to calculate, to understand any kind of superconductivity, or what are the limitations?
Just electron phonon superconductivity, okay? All the other things that people like to study, all the mechanism, all the materials like the cuprates and everything, it's not. All that was done for electron-phonon interaction. Okay, so conventional superconductors with strong electron-phonon coupling. Okay?
Hi, thank you very much for the nice results. So 2D materials are interesting for a lot of reasons. One of them, in my opinion at least, is that they are highly manipulable. Okay, so we can strain, we can bend, and have you any guess of what would happen to your TC, for instance, if you dope the material with a gate? I know that you can do that with DFT, putting charge, extra charge there, but do you have any sense if your DC is going up or not?
We haven't looked at that. We haven't looked at, because at this point, we were interested in trying to understand this material, because before there was that calculation that gave 16 Kelvin. They just calculate the electronic structure, no interpretation, nothing. They didn't talk about electride states, anything of that. And they calculated TC. Okay, so, okay, it's important information, but we did a lot better by doing the full Eliashberg equation, because we considered that anisotropy was a very important aspect of this material. And the interesting thing is that, as you know, this two-dimensional materials can be used for devices. You could use it using the strain to change the transition temperature if you wanted to do some kind of device. So there are interesting possibilities. And since we are interested in superconductivity, the aspect that we looked was the superconductivity of the material. But there are so many interesting questions in these two-dimensional materials that, well, some of them have been discussed here in this event, many talks.
Yeah.
Okay?
Maybe one thing that could be interesting to do regarding this doping is like putting other layer of another material next, like doing an extra structure. And so you, you wouldn't have the problem.
Thank you for the idea.
Of course,
it's interesting. That
gets more expensive, but
yeah. Thank you. Silvio.
I thank you for your last talk. Really a very good overview of the problem, okay? That's really fine. Let me ask you just one question about this pressure, okay? What's the meaning of 270 gigapascal, right? If you, are we going to be able to reach these pressures?
That's the...
Or just in... we have a talk here.
I have a surprising answer for you. I was surprised. You see, the Sirius machine in Campinas, they have a low material science division there, because they do all kinds of things, but there is a material science. Do you know what they do? High pressures and high tensions. And they told me that they go beyond 300 easily with these diamond anvil cells. I visited them recently, talked to them. They are interested. He said that a student will try to do the lithium-5 carbon. So go to 400 GPa is possible in many labs in the world, and they do that in a lab 3 kilometers from my office. And I only found that after I had published the 2 papers. Harry Westphal, the director of the series, gave a colloquium and showed the results of pressure and transition temperature. I said, look, I'm doing that, so I have to talk to these people. So we are talking.
Okay.
Okay? So it's feasible. That's the beautiful thing about this pressure studies in superconductivity, is that now with these diamond anvil cells, people do this. There are many labs in the world that do that. Okay? Marília. A Marília quer perguntar.
A única coisa okay, so the only thing is that you said that it is not stable at 0 pressure. So how do you build it?
The experimentalists, surprisingly, do that. What they do, they put the materials, the ingredients, in the cell. They pressure it, go to the pressure they want, and they give a laser pulse, very intense laser pulse that melts everything. And then at the end of that, they go there in the synchrotron, do the measurements, see if they produced any structure. If they do, they are happy, and they do the measurements. They even, that's another thing that I find very, very complicated to understand, but they do. They also put electric connections in this kind of cell, yes, and produce the material, and the material is connected to the wires, and they measure conductivity. If not, they measure magnetic field. Okay? So it's all very sophisticated, needs synchrotron, needs all these anvil cells that they tell me that sometimes, most of the times, they do the experiment one time because the diamond cell breaks. Okay? So it's all very, very tricky, and I'm always very, very impressed by what they do. Now that I can talk to the experimentalists and learn these things, no, I'm very, very surprised what they do. And it's surprising that they are doing that in Campinas. This is beautiful.
Okay, let's thank Professor Edson again.
Thank you very much. Thank you.
And our next speaker is